Welcome back, grade 12s. We're now continuing with our fifth practice example. Again, we have seven. I think there's an eighth one, but it's really short. So let's continue. All right, so we're looking at this question now. We're going to calculate the pH of a 0.1 molar solution of acetic acid with a Ka value being 1.8 times 10 to the negative 5. Okay, so we're looking for pH. We have a concentration. Right, the Ke value of acetic acid is 1.8 times 10 to the negative 5. Let's put all of this together. Okay, so what is pH? Okay, we have that the concentration of acetic acid is 0.1 moles per liter. We have Ka, also given to us 1.8 times 10 to the negative 5. All right, remember our Ka expression, I'll put it off to the side. Our Ka expression is okay, from the ionization of this acid, this weak acid. Okay, so here is, again, when in doubt, make a nice table. Usually, if it doesn't solve it for you or help you solve it, it helps you organize your information. Okay, so here is your ice table. So acetic acid, water. Hope I gave myself enough room. Okay, I should write states, but it's going to get messy. Write states. Okay, so ice table, 0.1 molar concentration, right? Straight from the question, we know we can cross out water there. At time 0, we know that these have 0 concentrations. Then we have this decreasing by a certain value. Don't know what that is. It's x decreasing, so minus x. It's all a 1-to-1 ratio, so this will increase by positive x, and this will increase by positive x. At I and C, right? You've seen this many times now, and we get these expressions at equilibrium. Okay, we then plug that in. Our Ka expression, we know what Ka is. It's 1.8 times 10 to the negative 5. Okay, we know, or at least we have expressions. We don't know these values yet. We have expressions for these, right? So that, from our ice table, it looks like this. And then minus 1, sorry, 0.1 minus x. Okay, we can solve this, right? We can solve this. Go ahead and expand. I'm skipping 2 or 3 steps here, but what you get is this. Go ahead, see if you can test for the hundreds or 5% rule. I'm going to plug this into our quadratic equation. So x, again, we know we're going to have a plus or minus value here. Negative b plus or minus the determinant, b squared minus 4ac. I'm not going to do the whole thing because you guys can do this yourself, right? That is going to do this one last step for you, and then I'll give you the x values. Okay. Right, so plus or minus, we get 2 values. X is going to be 0.001332. Again, keep as many digits as you can, at least 4 or 5. Or, I'm not going to write it down. Or some negative value. Now, it can't be negative in this case because having a negative X value would mean you have negative concentrations for these ions, for hydronium and for your acetate ions, and that can't be, right? So you can't have a negative value. I'm going to write not possible, just to be clear. Okay, so therefore x is equal to 0.001332. Okay, now it's asking, if you recall, it's asking us what the pH is. Well, to figure out pH, we know that we need a negative log of the concentration of hydrogen ions. And if we know what x is, that means we know what the concentration of, we know that it can either be, I'm interrupting myself, but hydrogen ions are the same as hydronium. So we now know how to figure out, or have enough information to figure out what pH is. So pH is equal to the negative log of the concentration of hydronium ions. We now know the value of, right, this is the concentration of our hydronium ion. Okay, so negative log and we have this pre-calculated 2.87 as our pH. And you're all set. Okay, so that's the answer. Don't know about sig figs, but you can figure that out. Moving on. That's question 5. Okay, question 6. Let's see. Here it's similar. Here we have a Kb value though, so we're looking at a base, hydrazine, and here's a formula. So Kb for hydrazine is 1.7 times 10 to the negative 6, and we have a concentration. Again, we're being asked to figure out pH. Okay, so let's do that. I'm going to need room, so I'm going to erase all of this and scroll up. Okay, so again, we're being asked for pH. All right, we're given guess didn't have to write aqueous if we're talking about concentration, but there you go, 0.1 moles per liter. All right, so this is going to behave like a base. We're going to have to write an ice table and therefore an ionization expression or reaction. But just making sure now to just write down everything we're given in the question so we don't have to toggle back and forth. Okay, so here's how this base will behave like a base. We know that this occurs in water. Okay, and remember, bases, you might wonder, what am I going to do with hydrazine? I've never seen this before. How is it going to react? Just, you know it's a base. You're given a Kb value. This base is going to accept a proton. It's going to behave like a Bronston-Lowry base. So we're going to get N2H5. That's it. And that comes from H2O, which means we have this conjugate here now. And ice table. Okay, from the question, point 1, line right through water, 0, 0 times 0, negative x, all proportional to their coefficients. Okay, our Kb expression, we know the value of, just jumping right into that, 1.7 times 10 to the negative 6, x times x over 0.1 minus x. Okay, so we didn't in the last example, but we're going to do this here. Okay, we're going to ignore the minus x since Kb value is very small and it passes or it follows the hundreds rule. Okay, you can check this out yourself. Take this number, multiply that by 100. Is that still less than the initial concentration given to you? It is. It passes the hundreds rule. You don't have to show me all that proof, right? Back in our lesson over about low K values, I showed you how to prove that. You don't have to each time you employ the hundreds rule. Just, you do need to, though, say that you are getting rid of that minus x because of it. Okay, so let's scroll down. Okay, that allows us to do something that looks like we're cheating, but we're not. 0.1 times 1.7 times 10 to the negative 6, we've gotten rid of that negative x. What we get is x squared at the top, and we get 1.7 times 10 to the negative 7. Solving for x, we root both sides. I like to read x's left to right, so I'm going to write this. X is equal to 4.12 times 10 to the negative 4, okay, which we know, right, is going to be our hydroxide concentration, right, at equilibrium, right here. Okay, so that's equal to, according to the ice table, hydroxide. Good, so now we have the concentration of hydroxide, and look, we're being asked for pH. We're getting really close to solving, to finishing this question. I can just figure out how to scroll down. Okay, scroll down. Okay, so this is our hydroxide concentration. There are two ways to do this. One is the easier way, one is a harder way. But one of the ways, the harder way, is preparing you for something that's coming up next. So I'm showing it to you now, and if you cringe at it, you can ignore it and just choose the easier way. But I want to show it to you now so at least you're exposed to it, so when we do it next week, it's not completely new. Okay, we know that Kw, I know where did Kw come from, but we know that Kw is equal to right? It's a self-ionization water constant equal to the concentrations of hydroxide times hydrogen. Okay, if we know one of those concentrations, right, hydroxide in this case, we can plug that in. 4.12 times 10 to negative 4. If you haven't already realized, this is probably the way that I said was going to be the harder way, or just the very, it's not hard. It really isn't hard. It's just different. You haven't seen it before. Okay, so Kw we know is 1 times 10 to the negative 14, our water constant. And then we just solve a bit of grade 11, not grade 11, bit of grade 9 algebra here. We get H is equal to 2.427 times 10 to the negative 11. Very small, right? So it's probably not going to have a very low pH at all. Okay, so that's that. Now that we have the concentration of hydrogen ions, we can figure out pH, and pH is negative log of the concentration of our hydrogen ion, and that is negative log of 2.427 times 10 to the negative 11, and I have enough room, just barely. It's 10.61. That is our pH. Okay, so that's one way. That's one way. Okay, or the other way. That's a nice color. Okay, or the other way. We have POH, right? So, well, we're going to figure out POH because we have concentration of OH. So that is negative log of the concentration of OH right? And we get a POH value of 3.38, right? We can figure out pH because it's 14 minus POH, which is 14 minus 3.38, which is 10.61 is our pH. And look, let me fix that 6 over there. It's the same. So two ways, choose either way. They both will work. Okay, hopefully that was okay. Couple more examples. You're rolling your eyes right now, but that was the longest one. Okay, let's start. All right, so here, a sample. This introduces the kind of question it is. Let's just jump into it. A sample of a 0.1 molar concentration of hypochlorous acid, HOCl, has a pH of 4.23. It's asking us to calculate Ka. Okay. Erase all that. Okay, back to yellow. So let's write down what we have. Hypochlorous acid, given concentration, moles per liter. We need to find Ka, right? It's asking us for that. And how do we do that? Well, we know from the ionization reaction, which I will write in just a moment, but to give you a preview, our Ka expression for this acid looks like this, right? So this is, if we can solve for all of these at equilibrium, we know what Ka is, right? We also are given pH. pH is 4.23. Okay, so now we don't have to toggle back and forth. So our ice table, HOCl in the presence of water will ionize, and we get these ions, hydronium, because it is an acid, and its conjugate base. Okay, so ice. Okay, point 1, ignore water, 0, 0, right? You can probably do this part with your eyes closed. Okay, Ka, we know our Ka expression. Now, here's a clue. pH is given to us. This is the pH at equilibrium. Well, these are our expressions at equilibrium. In the easier equilibrium questions you did last week or 2 weeks ago, they would give you one of these values. At equilibrium, you get this concentration of whatever product or reactant, and then you can figure out what your KEQ is. Here, it's essentially the same. One added step, though, they did give you the pH, which will tell you what the hydronium concentration is, or can tell you, right? To do that, all we need to do, remember that the concentration of hydronium is base 10, or 10 to the negative pH. So 10 to the negative 4.23 is 5.88 times 10 to the negative 5. Okay, since this is the concentrations, right? So this is the concentration of hydronium, right? Then that means therefore x is equal to, maybe there should be a sin statement there, therefore x is equal to 5.88 times 10 to the negative 5. Okay, and we're almost done. We know what the x value is. Just we had to do this was one calculation here. So let's finish this off. My scrolling isn't working. Okay, it's not working. Ka. Ka is, from our equilibrium expressions here, x over 0.1 minus x. I have to continue sideways. I wanted to go down. Oh, there we go. Too far. Okay, perfect. Good. So we know what x is, so just x squared, 0.1 minus, now that we know, of course, what x is 5 points. Oh, we should have just plugged it in here. Let's just plug it in. Save us some time. Okay, do all that math, and you get 3 times 10 to the negative 8 as your Ka value. And you're done. Okay, this was a pretty straightforward K equilibrium question, like a KEQ question you saw, one of the first types you saw, except what was different here is you're given pH, which is indirectly a measurement of the concentration of hydronium ions at equilibrium, which allows you to then solve for values at equilibrium, which you can plug into your Ka expression and solve for Ka. Okay, good. That's it. Last example. Promise it's not going to be too hard or too long. Okay, switching gears a bit. Polyprotic acids. We've looked at monoprotic acids, and we're going to continue focusing on especially acetic acid, but polyprotic acids we know are acids with more than one proton, and they dissociate one proton at a time. The point here is that each of those ionizations happen at their own separate, own different Ka values. The largest Ka value, even for a weak acid, is going to be the first Ka. So compare 1.7 times 10 to the negative 2 to the second Ka value of the second ionization, and you can see it's 6 orders of magnitude different. So it's always easier then to remove the first proton in a polyprotic acid than the second one. A few things. They continue to decrease as more protons are dissociated. Okay. If an acid is strong, Kas are both large. So if it's a diprotic acid, both Kas are going to be strong enough or high enough to make it to define it as a strong acid. Um, so they will happen quickly enough, and therefore they are considered strong acids. So if the acid is weak, each equilibrium constant must be taken into account. I guess to be meticulous about it, what we will do is we will only take the first Ka value into account unless you're told otherwise. Okay, so we're going to write, says the ionization of a weak acid such as arsenic acid looks like this. So this is a diprotic acid, and the ionization of this just looks like this. So you can probably do this yourself. I'm going to do it together with you. Oh, I'm going to switch though. Okay, so arsenic acid. Okay, the water is implied by the AQ here. Just another way. Um, this does go back and forth, so let's just do that. Right? First ionization, first removal, and that has a certain Ka value. The second ionization comes from here. Okay. And our Ka of the first ionization is 5.0. I would not expect you to know this, but I'm just sharing this with you so that you can, so I'm just trying to drive the point home that the first ionization is always greater than the second or third or others to come. Okay, so really this would have just been the answer to that question. This you wouldn't have known. I wouldn't expect you to know. But again, it's the first ionization is always greater, and that's the full ionization of arsenic acid. Okay, you don't have to memorize this. With the student's permission, he said something I thought it was last year. Yes, it was last year. It said something that was quite well put. So he says, when calculating pH, only use a first dissociation, ionization, perhaps should have said, and related Ka1 value. Now, all of these are just more examples. Notice that the table is not in blue. You do not have to memorize this. If you ever need to know the different Ka values, they will be given to you. And that's it. Hopefully that helped. Post any questions.